so I think we're gonna go ahead and start. So I am gonna go over the fall 2019 practice exam. It's the one in your notebook, and it's also posted on the website with the key and everything there. As usual, I don't have the key with me, so stop me if I make a mistake. We're just gonna go through the whole thing. Exam 3 is generally pretty quick. At least it's faster in general than the other exams. Students usually finish early, and students usually do pretty well on it. So hopefully this goes okay. So let's go ahead and start. Questions 1 through 3, we have this situation. It says we're looking at a 25 question multiple choice test that awards 4 points for each correct answer and subtracts a point for each incorrect answer. Okay, and there's 4 choices for each question, only one of which is correct. Suppose you guess at random and your score is computed. So this question is first asking, what would the box model be for this situation? So remember, box models are just a way to simulate random variables or situations where it's similar to drawing tickets out of a box. So in this case, we could pretend that each of the questions are the scenario of drawing tickets out of a box. So I would say, because it says you guess at random, this is definitely more of a gambling game situation than a survey. So here for gambling games, we always want to draw the box for one play or one draw in this case. In this case, I guess it would be one question because it's a test. So I would say for one question, there are 4 answers, right? Yeah, 4 choices. So I'm going to have 4, oops, here we go, 4 total tickets in my box. 4 tickets. And then I drew this, hold on, I drew this kind of small. Let me draw a bigger box. 4 tickets, and then each of the tickets represent your score for the question. So it says there's one correct answer and you get 4 points for that. And then you get -1 points for every incorrect answer. So my box, wow, I did not do a good job of drawing this, but hopefully you guys can see it. The box has 4 tickets, 1 marked 4 and 3 marked -1, which looks like that is C. And your score is just the sum of drawing out of that box 25 times, because this is a 25 question test. So that is also C. So we can think of this test as randomly drawing out of that box 25 times and adding up our tickets. Here the draws are definitely going to be with replacement, because that's always the case for gambling games. And for a test, if you get the answer right on the first draw, you could get it right on the second draw too. So if I drew without replacement in this case, I'd actually run out of tickets. So this one has to be with. All right, hopefully so far so good. The next 3 questions, it looks like, are another situation. This is for roulette. So it says, suppose a gambler plays roulette 100 times. So that is my N, just like my N in the previous scenario was 25. And let's see, this is roulette. So it looks like it's a pretty standard game of roulette. If the ball lands on red, you win $1. If it lands on black or green, you lose $1. So here again, this is definitely a gambling game. So I'm going to draw the box for, in this case, I'm going to say 1 play, 1 draw, same thing, 1 spin of the wheel. And for the roulette wheel, when I spin it once, there are 38 options. So there's going to be 38 tickets. Roulette is pretty much, if it's a standard game of roulette, there's always 38 tickets. And then you can either win, so you can either win $1 or lose $1. And then there's a bunch of different ways that can happen. So if you land, it says if you land on red, you win $1. So there's 18 ways to win, 18 red slots, and then the remaining 20 slots are the losing slots, so you would lose $1. So which one is this? This is D, right? Yeah. Okay. That looks good. And then the gambler's winnings correspond to the sum of 100 draws in this case. So that's a question. The test that you guys are going to see on Wednesday, I have some multiple choice, some fill in the blank. And for the number of draws, I made most of those fill in the blank. So your number of draws is just how many times you're playing the game, how many questions are on the test, how many times you're rolling the die, whatever the situation is. Okay, and then again, for gambling games, it's always with replacement, because for roulette, if you're actually spinning the wheel, you can't remove one of the slots. And you spin it and get a 1 on the first play, you could get a 1 on the second play as well. So with these, yeah, I just recommend going slow and kind of thinking about, is the situation a gambling game or is it a survey? So we'll get to the survey questions later, but these were 2 gambling games. And I'll see if anyone has any questions. No questions so far. That's good. Okay. All right. So there's a question like this on your guys' test on Wednesday. It says the 3 histograms below are the probability histograms for the sum of 23, 79, and 146 random draws with replacement from a box that contains 49 tickets marked 0. Okay, so we have a box that looks like this. We have 49 zeros and 1 ticket marked 1. So there's 50 total tickets in this box. It is definitely lopsided. And that means with lopsided boxes, it's going to take more draws for the histogram to look normal, the probability histogram for the sum of the draws, or average or percent. In this case, it is sum. So I am going to match these up by saying the one that looks the most like the normal curve has the most amount of draws. So in this case, that is histogram C, right? So histogram C should be the 146. And then the one that looks the least like the normal curve is going to have the least amount of draws. So I would say between A and B, B looks the least like the normal curve. So B should be the 23. And then histogram A is kind of in the middle. So that should be the 79. So lopsided boxes need more draws to look like the normal curve. And then as always, the more draws we have, the more bars. So that's another way I could have thought about this problem. But either way, that looks good. Looks like still no questions. Good. Hopefully that means you guys feel okay about exam 3 material. The very last couple questions on here are pertain to tossing a fair coin. This, if I look at it, it says we're first tossing the coin 100 times. They give us the expected value in standard error for the sum and the percent, and it says now suppose you toss the coin 3,600 times. And then it's asking, how does that affect the expected value in standard error? What happens when we increase our number of tosses? So here, this problem, because we're looking at how does n affect the standard error and the expected value, I would say this problem is involving the law of averages. And the law of averages was, I think it was from maybe chapter 15 or 16, and it says that as n increases, as n goes up, my standard error for the sum increases, and my standard error for the percent or the average decreases. So this just comes straight from those formulas. You can look at them where n is in the formulas. As n goes up, for sums, the standard error gets bigger, and for percents, the standard error gets smaller. So what I would do, I always like writing these out. So I would say, okay, my first scenario, I'm going to deal with the sums first, just because that's what 10 and 11 are for. So for the sums, it says my expected value for the sum is 50 heads, and my standard error is 5. So I can write this as 50 plus or minus 5 heads in 100 tosses is about as likely as blank. They don't give me the expected value or standard error heads in 3,600 tosses. So I'm just kind of rewriting what they gave us. there's a question, what variable do they go up and down by? So that's what we're going to talk about now. So as n goes up, they go up and down by the square root of n is what that is. So like in this case, we can see n is going from 100 to 3600. So it's increasing by a factor of 36. And so that means that my standard error is going to, for sums, it's going to go up, so it's going to increase by a factor of 6 of the square root of 36. So my standard error right away, I can say if n goes up by 36, my standard error for the sum goes up by the square root of that factor, which is 6. So this should be 30 for the standard error. I kind of skipped expected value first, but standard error scales by the square root of n. So I guess I can circle that. And then the expected value, it depends on what you're dealing with, sums, averages, or percent. So for sums, if we're tossing the coin 100 times, our expected value is 50. So that means we'd expect to get half heads. Same thing for 3600. We're still expected to get half heads. So if I toss a coin 3600 times, my expected value of heads is 1800. So for sums, I always just like to think of the expected value as half of the n, no matter what. Like if I tossed a coin 1,000,000 times, the expected value would be 500,000. In other words, it does increase by a factor of 36 as well. But I think it's easier just to think about if you toss a coin however many times, how many heads are you expected to get? So that's scenario number 1. That's for sums. Let's think about this for percentages. So let's do percents next. And I'm going to actually write the same thing because it's the same situation. They give us at the top the expected value for the percent is 50%, plus or minus 5% heads in 100 tosses is about as likely as blank, give or take blank percent heads, again in 3,600 tosses. Okay, so we see again, n is still going up by a factor of 36. So for my standard error, in this case, the law of averages says, if we look back at the top, the law of averages says as n gets bigger, the standard error for the percent goes down. So I'm actually going to be dividing instead of multiply for percents. So in this case, I'm going to divide by, again, the square root of n. So I'm going to divide by 6. So my new standard error is going to be a decimal. It's going to be 5 divided by 6, which is 0.83%. And then for the expected value, again, I just like to think about it without a formula and say, okay, if you're tossing a coin 3,600 times, what percent heads do you expect to get? You're always going to expect to get 50% heads. I'm trying to get perfect thickness. Hopefully that's good. But yeah, so for expected values for sums, for a tossing coin, it's always going to be half. For percents, it's always going to be 50%. And then the standard error changes by a factor of the square root of whatever n is changing by. So that's the law of averages. Let's see. So this one is 50% and this one is 0.83%. So any questions on the law of averages? Okay, if there are no questions, we'll keep moving on. The law of averages is going to come up a couple other times throughout this exam, just that idea that change in n results in a change of standard error. So I'll point that out when it comes up again. So would we get a question with 60%? Somebody asked. Oh, that's a good question. Not for a coin toss. I guess that would be an unfair coin, but I wouldn't do that to you guys. We've only done fair coins for the for the practice and the notebook. So that's the one on the test is going to be pretty similar to this. The biggest thing is to regardless of how these are written, to be able to say, okay, this is asking me as n changes, how does that affect my standard error and expected value? Yeah, you could have a non-fair coin technically, but to keep it simple, I'm going to have a fair coin every time. All right. Okay, looks like we're good. What is going on here? The 4 histograms below in scrambled order are the probability histograms for the sum of the draws from box A. So here is box A. It looks nice and normal, nothing weird about it. And then 2 draws from box B. Here's box B. It looks a bit lopsided. Actually, I think these 2 boxes were the exact same ones in the notebook. So they might look familiar, and then 25 draws from each. And we want to go ahead and match these up. So what I would do first is figure out the number of draws. So the more bars, the more draws, right? So histograms 1 and 3 definitely have the most bars, right? So these are going to be 25 draws for sure. And then histograms 2 and 4 are going to be for 2 draws. So I always like to get that out of the way because then you're double checking. Or that, I guess then you're making it so that you only have to choose between 2 instead of 4. So histogram 1 we know corresponds to 25 draws, and then the question is it box A or box B? And compared to histogram 3, the other 25 draws, it looks way more like the normal curve. So this one's going to be from A, and this one's going to be from B. And then the same thing with histograms 2 and 4. If we look at them, histogram 4 looks way more like the normal curve, so that's going to be from the nice normal box. Histogram B doesn't look like the normal curve, so that's going to be from the lopsided box. So then I would just fill these in. Histogram 1 is 25 in A, right? And then histogram 2 is 2B, histogram 3 is 25B, and histogram 4 is 2A. And then it looks like somebody asked, is 10 C or D? Let's see, what was 10? 10 is going to be D because it's for the sum. So it's like how many heads do we expect to get? If it was percents, the answer would be C. But because it's sum, we'd expect to get half heads for 3,600 tosses. Okay. Another way, I'll just give you guys just another way to solve this too if you wanted to. At least for the two draws, what you could do is think about, like box B, if I took 2 draws out of box B, the smallest sum I could get is 2 ones, right? The smallest sum would be 2. And the biggest sum I could get is 2 nines, which is 18. And if I look at histograms 2 and 4, histogram 2, the bars, the lowest one is at 2 and the biggest one is at 18. So I know that has to be for box B. Whereas box A, if I draw 2 times out of it, the smallest sum I can get is 2 ones, which is 2 right there. And then the biggest sum I can get is 2 threes, which is 6 right there. So that's another way to think about that. Maybe that would help. But yeah, there's a bunch of different ways to do this. You can look at it, you can think about drawing out of the box actually. You could calculate the expected value if you wanted to for the 25 draw ones, but all of them work. All right. Any questions on that? Okay. If not, let's keep going. Next, we have 100 draws, so that's my N. Made from this box, there are 4 tickets, 1, 2, 4, and 5. And it says, what's the smallest the sum of the 100 draws could be. So this is kind of like what I was just talking about. The smallest sum technically would be getting a 1 every single time. So this is not likely, but it technically is possible. So if I got a 1 every time for 100 draws, my sum would be 100, right? 1 plus 1 plus 1 100 times. Same thing for the largest sum, I would get the biggest number every time. So the 5, getting a 5 100 times would be 500. Both of those are very rare. The chances of that happening are super small. Instead, what's probably going to happen is we're going to get somewhere around the expected value. That's what expected value is. It tells you what are you expected to get if you do this over and over again. So the expected value for the sum is just n times the average of the box. So n in this case is 100. And let's see, the average of this box, if I add these up, I should get 4, right? 3. Why can't I do math? 12 divided by 4, 3. I should get 3. So then that would be 100 times 3, which is 300. That looks good. And then the standard error is the give or take. So this idea of when we draw out of that box 100 times, we're expected to get around 300, but because we are doing it randomly, there's this idea of chance error. So it's better to give a range instead of a point estimate of 300. So let's go ahead and calculate the standard error for the sum, which is the square root of n times the SD of the box. And n is still 100. SD they're telling us is 1.6. So I'll give you guys, if you can't do the shortcut formula, I'll give you the SD of the box just because we already tested on how to find the SD. And honestly, I don't know anybody that does it by hand. Like, you'll probably be able to do it with software or a calculator at least. So yeah, that's why we gave that to you. And then this ends up being 16, right? 10 times 1.6. That looks good. And what I would recommend actually on Wednesday is for you guys to have a list of the formulas. I think in the video, actually, I don't know. I can't remember if I did this. I thought I made a list of them in the video, but maybe I didn't. But anyway, I can, if it's helpful, I can make a list of them at the end of this review. But I would have the formulas right next to you when you're taking the test, so you don't have to like go searching through the notebook. This is one good thing about being online, I guess, is that the tests are open book, so you don't have to memorize all these formulas. But to be honest, now I'm thinking I shouldn't even make students memorize them because the exam scores are pretty much the same regardless of if you memorize them if you don't. Anyway, that was a side tangent. Let's keep going. Any questions? The video we made, okay, good. I thought so. There's a list in the video. Perfect. Thank you, Agent Bubblegum. Okay. Just waiting a couple more seconds to see if there are any questions. All right. Next, it says, for the following questions, convert the same box, so this guy right here again, and count the number of even numbers, and use the new box to answer questions 22 through 27. So, okay, I'm going to switch this to a 0, 1 box, because now I don't care, did I get a 1, did I get a 2, did I get a 4 or a 5, I just care, did I get an even or not? So if I was going to do this, 1 is not an even number, so I count it as 0 evens. 2 is, so I count it as 1. 4 is, so I count it as 1. And then 5 is not an even number, so I count it as 0 evens. So I'm counting all of the even numbers. It looks like the box would have 2 zeros and 2 ones. cool. How many even numbers would you expect to get if you drew 100 times from this box? So here I could use the expected value of the sum formula if I wanted to, just because it doesn't say average or percent. I can assume I'm dealing with sums, counting up how many evens I get. Or I could say I know there's half ones and half zeros, so half even numbers and half odds. So I should expect to get 50. It's kind of like a coin in this case. If you wanted to go ahead and do the expected value for the sum formula, it would be n times the average of the box. The average of this box is, let's see, 2 over 4, right? 0.5. 1 plus 1 over 4. So it would just be 0.5 times 100 is another way to get that 50. But with these, I don't know. I don't know what students think, but I always like to think about it rather than using the formulas. If I don't have to use the formulas, that's good. But maybe you like them. All right. Cool. Thank you guys for saying the list of exam 3 formulas was written out in the chapter 15 and 16 lecture video when we finished. It was right after we finished doing all the formulas was when we wrote them out. Okay. I like them because I can't think. That is definitely a mood in 2020. I hear you on that one. All right, what else do they want here? What is the SD of the box corresponding to the total number of evens? Okay, if you draw 100 times. So the SD of this box, basically, this one right here. So I'm going to use the new box to answer all these questions. And so the SD here, I could use the shortcut formula if I wanted to, or I could say the box has half ones and half zeros. So if that's the case, then the SD is going to be, I know it's going to be 0.5. That's always the case if a box has half ones and half zeros. So that might save you some time on the exam. If I wanted to go ahead and do the shortcut formula, I could just say the absolute value of 1 minus 0, because I have ones and zeros, times the square root of the fraction of ones is 2 over 4. And the fraction of zeros is 2 over 4 as well. And that gives me 0.5. So you can always check yourself with the formulas. Looks good. What is the SE of the total number of evens you'd get if you drew from this box 100 times? All right, so the standard error, basically this question is asking which standard error should I use? And the question is it sums, averages, or percents? And here it's going to be sums, just because no mention of average, no mention of percents, and we're counting up how many evens we get. So standard error for the sum is SD times the square root of n. Which one is that? This one? E? Yeah, SD times the square root of 100. Next, 26, what is the percent of evens you'd expect to get if you drew out of this box 100 times? So again, this box up here, and because there's half evens, I would say this is 50%. Here, the formula for expected value for the percent is just the percent of whatever you're looking at in the box. So the percent of evens in the box. So in this case, there was 50%. If there was one even number, the expected value would be 25%. And then for standard error for the percent, this is again, I guess, do you know this formula? SD over root n times 100. So n is 100, so this should be D. I guess here we were trying to make it so that if you got the SD wrong, you wouldn't get these other ones wrong too. Cool. Done with that. Okay, for the same box shown to the right, the expected value for the percent of ones in 100 draws is 25%, and the standard error is about 4%. Okay, so now we're only concerned about the ones. That makes sense. EV percent is 25%, and then SE percent is 4%. So they gave us that. And then it says if I wanted to calculate the probability that the percent of ones is less than 30%, so I'm expected to get 25%, we're saying what's the probability I get a number less than 30% if I draw 100 times, what would the z-score be? So here, I'm going to use my new z-score formula for random variables. So our old z-score formula was value minus average divided by SD. New z-score formula is value minus expected value divided by standard error. So the difference between this and our other z-score formula, our other z-score formula is just for a list of numbers. If we just have a data set and there's no element of chance, we're given the data and we know exactly what it is. Whereas in exam 3, now we're talking about this idea of chance numbers and random variables. So we don't have an average per se and an SD per se. Instead, we have these expected value and standard errors. But they're very, very similar to the average and the SD. So hopefully that distinction is clear. Sometimes people ask me on the final, they're like, how do I know which z-score formula to use? And it just depends. Are you dealing with box models? If so, use this one. Or are you dealing with just data? Then use the other one. So let's see, my value in this case, my value is 30%. My expected value I know is 25%, and then my standard error is 4%. So 5 over 4 gives me 1.25. So interpretation of this z-score, this means that, let me go ahead and draw my normal curve. This means that if I get 30% ones, if I draw out of this box 100 times, I'm 1.25 standard errors above what I would expect. So here's 0. 0 is my expected value, which is 25%. And then 1.25 right here, this represents getting 30% ones. So 29 is asking me if I wanted to calculate the probability that the percent of ones in 100 draws is less than 30%, what would the chance be? So I'm going to go ahead, I drew my normal curve actually already, and then I'm going to shade everything. Oh no, oops. Sorry you guys. I meant to do a shading and I did the eraser there. This is what I wanted. I'll do it, I'll make it green. Here we go. So I want everything below 1.25. Okay, so we've done the normal curve on exam 1, exam 2. Hopefully this should look familiar. If you need to find an area on the normal curve, we know that we can look up the z-score. We can look up 1.25, and that will give me the middle area between negative 1.25 and positive 1.25. So I think I have a normal table attached to here. You guys will get the normal table. 1.25 is right here. It looks like the middle area is about 79%. So if I go back to right here, this is 79% in the middle. That is one of the answer choices, but that's not my answer. My answer is all the green shaded area because I want everything less than 30%, all the area to the left. And then, okay, so that means I need to find this tail. To get this tail, I would just take classic tail formula, 100 minus the middle area minus 79 divided by 2. So that is 100 minus 79 is 21, divided by 2, 10.5. And so my answer should be 89.5%. Should be this. So hopefully normal curve you guys feel okay with. It'll come back again after exam 3 as well. So there'll probably be, I think there's only one question about the normal curve on exam 3. Let's see. Thanks to the stats class, I like math better now. Oh my gosh, I love that. Honestly, thanks to stats, I like math better too. I've always liked math, but stats is just, I love the applied appliedness of stats, it's the best. That's so nice. Thank you. When you know what you're doing, it's a lot more fun. Yes, I completely agree. I didn't really like math classes in college because I felt like I never knew what I was doing. All right. So we don't change the z-score to a negative because the answer is positive. Here we don't need to change the z-score to a negative just because our value, which is 30%, is above the expected value. So if our value was something like, I don't know, 21%, that's below our expected value. Remember, our expected value was 25. Then we'd have a negative z-score. But here, we just want everything to the left of our z-score, which includes the middle area and the left-hand tail. So I'd always recommend drawing your picture. If you have a negative z-score, the area to the left is just going to be the left-hand tail. There's some math talk in the chat. This is funny. I like math without a lot of formulas. I was always scared of stats because I hated analysis stuff. This is easier. Oh, I'm glad you guys like stats. That's the best news I've gotten all week. It's only Monday. But anyways, let's go ahead and move on unless there's any questions. Okay. Looks like there's no questions. What else do we have here? Questions 30 to 35. A gambler plays roulette 81 times more roulette in this case. So now my N is 81. Here's my N. Betting on the numbers 1, 2, 3, and 4 each time. If the ball lands on 1, 2, 3, and 4, the gambler wins $8 or they lose $1 if it doesn't. Roulette wheel has 38 slots. So again, for the roulette, this is slightly different than the roulette question from before. But with the roulette wheel, if I think about one spin, there's always going to be 38 slots. So there's always going to be 38 tickets for roulette. So right away, I'm going to get rid of answer choice E. And now I need to figure out what is going on. So we're looking at how much we win and lose. Let's see. It says if the ball lands on 1, 2, 3, or 4, they win $8. So we always want to put the amount you win or lose on the tickets. So you either win $8 or you lose $1. And then I'm going to say how many. Right now it just looks like there's one of each. I'm going to say how many there are. So there's 4 ways to win $8, and then the rest, the other 34 numbers, you lose $1. So my box is going to be choice D. Okay, what else are they asking? This score corresponds to the blank of the draws from the box. So it's asking, are we dealing with sums, average, percent, and then how many draws are we taking? So number of draws is always our N, so that's going to be my 81. And then here, sum, average, or percent. I don't see anything about average. I don't see any percent signs, so this is going to be sum. Again, because we're adding up how much we win. So with gambling games, a lot of times it's sum. What is the average of the box? The average of this box, if I was going to calculate it, the average is just adding up all the tickets and dividing by 38. So here I would add up these 4 8s. You can also do 4 times 8. And then I would add up these 34 negative 1s. It looks like they didn't even simplify it. So whichever one looks like this. This one. I guess be careful with these. They all kind of look the same, but should be E. And then what is the SD of the box? So here we can figure it out using the shortcut formula because there are only 2 types of tickets. So remember, it's the absolute value of A minus B, so the numbers on the tickets. So in this case, 8 minus negative 1. So I know a lot of times when students are doing a question like this, they'll just go to autopilot and say 1 minus 0 because we do use a lot of 1, 0 boxes. But in this case, just double check. We don't actually have ones and zeros. I want to use those numbers on the tickets. And then times the square root of the fraction of a ticket. So the fraction of 8s, which is 4 out of 38, times the fraction of negative 1s, which is 34 out of 38. And then if I was going to put this in my calculator, I would do the absolute value part first. So 8 minus negative 1 is 9, and then times square root of 4 out of 38 times 34 out of 38. And that should give me 2.76, if I remember this question correctly. E again. Okay, looking good so far, nothing too crazy. Oh, 34 more normal curves. So they told us the expected value of the sum is about negative $4. That definitely makes sense for roulette because you are always going to have a negative expected value. You're always expected to lose. The more you play, the more you're expected to lose. And the standard error is about $25. It's very variable because sometimes people win and then usually they lose. So we want to know what's the chance the gambler will win more than $6. More than $6 in 81 plays. So again, we want to convert that to a z-score. So I'm going to go ahead and draw my normal curve. And then I'm going to convert 6 to a z-score. So here we're again dealing with random variables. So I'm going to use my new z-score formula. Value minus expected value divided by standard error. Somebody said was 31A. Oh yeah, I didn't, oops, thank you. I didn't circle it. Yes, 31 was A. Thank you. Oh, and I love that you guys like stats. I keep saying that, but I really do. Okay, where was I? Oh yeah, z-score. So my value that I'm concerned about is $6. I want to know what's the chance I win more than $6 in 81 plays. My expected value is negative 4, and my standard error is 25. What is that? 10 over 25. So I end up getting 0.4 as my z-score. So what that means is winning $6 is 0.4 standard errors above what I would expect. So here's 0, here's 1, 0.4 is like right here, and this represents, 0.4 represents winning $6. 0, my expected value, is losing $4. So remember with z-scores, the nice thing is we're in dollars, but we can convert dollars to standard units or z-scores, and then we can use our normal curve. And all right, so I answered the z-score question, and then now it says use the normal approximation and the fact that the expected value of the sum is about $4 and the standard error. Okay, to figure out the chance, they want us to figure out the chance that the gambler will win more than $6, right? I feel like this is actually helpful if you're playing roulette because you can set the amount that you want to win and calculate the chance of it. So I would, $6, I would say like, what's the chance I win more than $100? Probably really low. But here, it looks like the chance is not terrible. To figure this out, I would, again, first step, look up 0.4 on my normal table, and that would give me the area between 0.4 and negative 0.4, my middle area. I don't know that one off the top of my head. Let's see, 0.4 is 31. 31% in the middle. And then, but that's not my answer. That is an answer choice, but that's not my answer. My answer here is what's the chance they'll win more than $6? So just the tail this time. So this is going to be 100 minus 31 divided by 2. And I get 34.5%. So here, the last one, remember we included the middle area plus the tail. Here, because it's greater than, we're only including the tail, and I have a positive z-score. So that's why I would always, with these, draw your picture. You guys should have scratch paper. Draw a normal curve and just double check. Do I need to shade, including the middle area or not? So any questions? Cool. Let's go ahead and keep going. So questions 36 through 38, it looks like we're finally getting into the polling or sampling part of this exam. It says in November 2010, that's a while ago, the week before California voters were asked to decide on Proposition 19, whether or not to legalize marijuana. Okay, CNN and Time conducted a pre-election poll asking a random sample of 888 likely California voters. So that's my N. Will you oppose or support Proposition 19 to legalize marijuana in California? 53% of the samples said they would oppose. All right. Okay. So here, what is the standard error for the sample percent? I guess what I would do is first decide, can we calculate standard error? So remember, if we did a bad poll, if we didn't use a random sample, we can't use any of our formulas. Here, it did say that we had a random sample, right? They asked a randomly selected sample. So that's good. That means we can calculate the standard error for the percent, and the formula is the SD over the square root of n times 100. So here we need to calculate the SD, and we can actually go ahead and do that because we're dealing with percents. Anytime we have percents, we can calculate the SD. So the SD in this case, we're asking a yes or no question. So it's going to be absolute value of 1 minus 0. And then we're going to do the square root of the percent of ones times the percent of zeros. So 0.53 times, and then we can assume, what was it? 53% of the samples said they would vote to oppose. So 47% must have said yes. So we can go ahead and do the calculation like that. And then this ends up being really close to 0.5. I think it's 0.499. Cool. And that is an answer choice, but that's not my answer yet, right? I'm like running out of room here, but I need to plug that in. So I have 0.499 divided by the square root of n is 888 times 100%. And that ends up giving me, I think it is this one, C, 1.675. Cool. So this one, just be careful. Remember, if it's not random, the answer would be not possible to calculate. Don't get too concerned about not knowing the SD. Ask yourself, can you calculate it or not? And here we can, because we know the percent of ones and zeros. Somebody asked how many questions are in the exam. I think there's 63 or 64. So Kelsey said around 60, which is exactly right, but a more accurate number, 63 or 64. All right, how did the election turn out? It says, for the actual election, the 54% of the nearly 8 million voters opposed the proposition. So we got in our sample that 53% opposed, and then in the actual election, they got 54%. So we were pretty close. We had a good estimate. And it says, which of the following statements best describes how good of a job the CNN random poll did in predicting the election results? So I would say here that we did pretty good, right? It was a 1% difference. A says the CNN poll was quite accurate since 54 is well within its 95% confidence interval. Yeah, we could calculate a confidence interval if we wanted to, but 1% is really, well, that's pretty good. This says it was off by 800 or 80,000 people, which was a huge error. I mean, 1% for a yes or no poll isn't a massive error. So, and then C says it's impossible to determine the accuracy. We could find a confidence interval and we would see that 54% is well within that. But this is kind of a weird question, but yeah, I'd say it's pretty good. What else do we have here? A similar poll was asked to a random sample of students at the U of I in 2019. Do you support the legalization of marijuana? So this was a survey I found, and 66% of the students said yes, and the standard error was 5%. What is an 85% confidence interval for the percent of students who say yes? All right, so we want an 85% confidence interval. And a lot of times, confidence intervals, I feel like, are one of those things that people think are more complicated than they actually are. All we want to do is take our percent that said yes, which was 66. We want to take this 66 and make it into a range. So we're going to add and subtract something from it. And for an 85% confidence interval, the z-score for 85% is going to tell me how many standard errors to add and subtract. So if I look up 85% on my normal table, the z-score is 1.45. So we're going to add and subtract 1.45 standard errors. If it was a 95% confidence interval, we've seen that one a bunch. We add and subtract 2 standard errors, but this is an 85% confidence interval. So A and C are like kind of, those are common wrong answers because people think like, oh, is it 85 plus or minus something? No, 85 is how confident we are. The actual number we got was 66%. So we want to figure out, we're 85% sure that if we polled all U of I students, they would answer between these two numbers. So which one is this? I guess we could find the standard error if we want to. It looks like the only option is the one, all of them have 5% as the standard error. So this one has to be B. But yeah, confidence intervals, you just take, to find any percent confidence interval, you just take your sample percent, whatever you got in your sample, and you add and subtract the z-score times the standard error. So this is called the margin of error. You guys may have heard that term a lot last week with the election. I heard them say margin of error all the time when talking about polls and confidence intervals. You definitely, if you're looking at data where it's close to 50% ones, 50% zeros, you want to have a small margin of error. But any questions on that? Cool. So yeah, it looks like we're into the survey part of the exam. So the exam's going to be about half like gambling game questions, and then about half surveys, poll questions. Okay. More polls. Let's see. This says this October. So this was a year ago for this exam. Oh, you might be wondering too, where's the spring 2020 exam 3? And spring 2020 was a crazy semester. We went online in the middle of the semester, and exam 3 was online. So I didn't have like a nice version of it. So that's why I'm using the fall 2019 one. Basically, it was on Compass. So yeah, but you still have 3 practice exams, so don't worry. 4, including this one. Okay. Anyway, back to this. Do you approve or disapprove of the impeachment charges against Donald Trump from fall 2019? A polling report poll asked the question of randomly selected adults nationwide, 1650. MSNBC Live and Fox News Live posted the question on their websites. Anyone who went there could go ahead and vote. And then I asked this question on bonus survey 3. So here are the results. We can see different sample sizes, different percents. Wow. These are all pretty different. It says which best reflects how all US adults would respond. Definitely the random poll, right? Random sampling is best. So the random one was the polling report one, right? Ask the question of a randomly selected sample. So I would say A. Not too bad, right? For each poll listed below, is it possible to calculate a 95% confidence interval for the percent of all U.S. adults who would say I guess, Donald Trump's impeachment charges was what it was about. So circle yes or no. So polling report. So here, all U.S. adults. That is the polling report asks adults nationwide. That's the same thing as all U.S. adults. So this one I'm going to say yes because it's random and we're talking about the same population. These other ones, like the two MSNBC Live and Fox Live, those are just on the websites. Those are not going to be super accurate for all US adults because they're only people who go to those websites. And if we look, actually, the Fox News Live one, this was crazy. 97% said disapprove. The MSNBC Live is a little bit different, but I guess they had more saying approve. So those ones we don't want to use any of our statistics because then we'd be lying with our statistics if we said that represented all US adults. And then bonus survey 3, our bonus surveys are like, they're fun and I like seeing the data, but they're not a random sample of all US adults. So I would say no to this one too. Honestly, they're not even a random sample of all students at U of I or even all students in Stat 100 because they're not random. They're extra credit. It's people who want the extra credit who are doing it. So, yeah. They're still fun, though. Speaking of bonus survey 3, I need to show you guys those results of bonus survey 3. We'll do that soon. Okay, any questions on this? So, random is best. All right, let's keep going. The next question, more polls. It says a CNN/Time poll asked a random sample of 1,250 adults nationwide the following question: would you be willing to allow a reality-based television show to film you drunk? I asked the same question as an iClicker question class last semester. Here are the results. Okay, so here we have two different surveys. This CNN Time poll was random, so I like that. The iClicker question was not random, right? Because again, it's whoever's in class, whoever answers. So, all right, if I had to pick which one is best for all US adults, I would say it's this one for sure. But the questions that this is asking are a little bit different. So, this one says, if I wanted to create a box model for both polls, how many tickets would be in the CNN/Time poll? All right, so the box models we can create if there's a random process. So for CNN and Time poll, this was random, so we could easily create a box model. For the iClicker poll, I'm actually going to say this one is impossible to create a box model because it's not random. And the whole idea of drawing tickets randomly from a box is where the box models come from. So we can't simulate the iClicker poll as a box model because it wasn't random. Okay. Now, for 44, the CNN Time poll, for this one, I'm just going to show my work up here. For surveys, which is what we have here, polls, we always want to draw the box for the population. And then imagine picking people randomly out of the population. So that's the big difference between the gambling games and the surveys. Gambling games, you draw your box for one single play. And then for surveys, you draw the box for the whole population and imagine randomly picking people. So the whole population for the CNN Time poll is adults nationwide. So my box is going to have millions of tickets because there's millions of people in the population. So that is A, right? That looks good. And then to get our survey, we'd imagine drawing 1,250 times out of that box. So n is 1,250. It doesn't ask us how many times we're drawing, but that's what it would be if that was the case. And on the tickets would be yeses and nos, right? Would you be willing to do this? So there would be a bunch of ones, a bunch of zeros. We don't know what all the millions of people would say, but we can estimate it to be 16% yeses and 84% nos. So I would say, if I was describing this box, I would say the percentages are unknown. But estimated from my random sample. All right. So if it has to describe the box, that's what we would say. Let's see, what does 46 say? As you can see, the results of the two polls are quite different. We have different percentages. Which survey gives a better estimate for the percent of all U.S. adults? We said that would be the CNN Time one, right? And that's because it was a random sample. The sample size, this says the sample size was larger. Large sample sizes are good, but in all cases, randomness is kind of better than sample size. So the randomness basically is the number one priority. And then we'd like the sample sizes to be big, but in this case, that's not the reason why it was better. That's not the main reason. What is the standard error for the sample percent of the in-class iClicker poll? So again, we have to ask ourselves, can we even do that? And here I'm going to say no, because it wasn't random. We don't know the size of the population. B says it's impossible to calculate, but we don't need to know the size of the population. We only need to know the size of the sample. And so this one wasn't random. So that's a good thing to keep in mind when you guys are taking the test on Wednesday, is to right away take, no, is the poll random? If so, then we can use all of our formulas. We can calculate a box model. If not, we can't really do anything with it. It might be interesting, but we can't do statistics and use it as an estimate for what we get for all U.S. adults. All right. That was it for this part of the exam. Let's go to questions 48 and 49. It says, pretend there was a third poll that was randomly drawn from all U.S. adults done by another polling agency. They took a random sample of 1,000 U.S. adults and got 18% of them answering yes to the same question. So it says our best estimate would be what? Then that would be 18%, right? The expected value for the percent is just the percent of yeses in the box. So here we don't know the percentage of yeses in the whole population, but we're estimating it to be 18%. So that looks good. And then it says, what would the standard error for the sample percent be? Here I can definitely calculate it because it was random. So I'm going to say I can use my formulas. So my standard error for the percent would be the SD over the square root of n times 100. This is another situation where they don't give us the SD, but we could calculate it because we're dealing with percentages, kind of like we saw earlier in this review. So what I would do is, I'm just going to do this all in one step. So the SD is going to be the absolute value of 1 minus 0, because it's a yes or no question, times the square root of, there were 18% yeses, which means there were 82% nos. So there's my SD. My n in this case is 1,000. And then times 100%. Cool. And then that gives me If I do this, I should get about 1.2%, I think. Yeah, 1.2%. So we'd expect if we ask all U.S. adults this question, we get between 18, give or take 1.2%. And that makes sense because if we look back up here, this CNN and Time poll had 16% yeses, which is inside that confidence interval. So that's good. The random polls, their confidence intervals matched. Okay. I'm checking for questions. Looks like we're good. Questions 50 to 53 pertain to this situation. It says, suppose the Ohio State University and University of Chicago both decide to poll their undergraduates. They want a margin of error of 4%. All right. The undergrad population at Ohio State is 9 times larger than the undergrad population at Chicago. So here it says for number 50, all other things being equal, you'd have to poll. The number of people you'd have to poll at Ohio State is how many times the number of people you'd have to poll at Chicago. So here, they both want the same margin of error. So they want the same accuracy. So we would just poll the same amount of people. So remember, this is the idea of, what did I call it? I think I called it the chocolate milk theorem or something like that. This is that idea that just because you have two populations that are different sizes, if you want the same accuracy, accuracy and standard error is just based on sample size, not population size. So you just take the same amount of students from both institutions, and then you'd want to make sure to look at the percentages instead of counts. So same accuracy. If you want the same margin of error, you're going to pull the same amount of people. The reason we called it the chocolate milk theorem is because we were saying, like, if you were taking a drink between two cups, one really big one and one small one, to see how the drink tastes, you just need to take the same sip from both of them. Population size doesn't matter in terms of accuracy. What else is this saying? How many people would you have to poll to get a 95% confidence interval with a margin of error of 4% at Ohio State? All right, so here I could either do this by the definition of the margin of error, or I could use the quick formula. We said we're kind of tired. We don't want to think, so I'm just going to use that, the quick formula, which is, it was 100 times the z-score times the SD divided by the margin of error squared. So this formula comes from, dang, I cannot remember the chapters. Usually I'm good at this. I think it was chapter 16, maybe 16. Check, or 15. It's in the notebook somewhere. And we go through the proof of it in the lecture video. But here, just to do it really quickly, I'm running out of room. Let's see. I would do 100. The z-score for a 95% confidence interval is 2. The SD, it says to assume to be 0.5, and then the margin of error is 4. So let's see, 100 over 4, 25 squared, right? This should be 625. And then 52 says, suppose you wanted to double your accuracy. So more accurate is, these I feel like it is kind of confusing, but to think about them, if you're more accurate, you have less error, right? Decrease your margin of error. How should you adjust your sample size? So if you want to be more accurate and have less error, you should increase your sample size, because we want our sample to be as close to the population as possible. So if we increase it, it gets closer and closer. So this one should be increase it. 53 says, how many people would you have to poll at Ohio State to get a 1% margin of error? And now they're saying assume your SD is slightly different. So again, I'm going to use that quick formula. I have 100 times, my z-score is still 2. My SD now is 0.47, and the margin of error is 1%. And this should give me, have to do math again. It should be D, 8,836. Cool. So these are just, they're a little bit conceptual with the accuracy and error, and how does that relate to your sample size, but then the quick formula is really nice for doing these. Any questions on that? Somebody said, why don't you divide by 0.04 in question 51 because it's a percent? So that's a great question. So this, because I'm using this 100 right here in my formula, we can just leave it as 4 for 4%. But if you got rid of the 100, then you would divide by 0.04. But because of that formula with the 100, we can just leave it as 4. But that's a good question. Anything else? Okay. What else do we have here? Is this my last page? Ooh, yeah, this is the last page. So next, it says a poll taken in Chicago asked a random sample of 625 brides from, so this may end, 625 brides chosen from all brides who got married within the last 2 years in Chicago. How much money did they spend on their wedding? Here's my average, and here is my SD. Wow, that is an expensive wedding. $72,000. Oh my gosh. Okay, so it says what most closely resembles the box model. So this is a survey. We could think of it as drawing tickets out of a box, drawing brides from this population, brides who got married within the past 2 years. And remember, with surveys, we always want to draw the box. Draw the box for the population. So all brides who got married in the past 2 years in Chicago, I would say that's probably like, thousands of tickets. I feel bad for anyone getting married now during COVID. It's so sad. Okay, so thousands of tickets, and then what's on the tickets is their amount, right? They're answered the question. So I'm going to say the average is unknown, but we can estimate it to be 72,000. So these two I'm going to get rid of because those aren't thousands of tickets. This one says the average we know is exactly 72,000. That's our estimate, but we can't say for sure. This one says ones and zeros. Nah, this isn't a yes or no question. It's got to be C. It has thousands of tickets. On each ticket is a dollar amount, and the exact average and SD are unknown, but estimated from our nice random sample. Random. Thank goodness for that. What is the standard error for the sample average? Let's go ahead and calculate it. We haven't done standard error for the average on this test yet, so formula is SD over root n. We've done standard error for sum and percent. This is the first time we're doing average. And the SD, it's technically the SD of the box, which we don't know, but the central limit theorem says we can use the SD of the sample, so $25,000. Remember the central limit theorem? I don't think I've talked about that, but that's why we've been able to use the normal curve for these problems, because as n increases, the probability histogram for the sum, average, and percent gets closer and closer to the normal curve. And then n, ooh, this, okay, I guess this wouldn't be very common because there's thousands of tickets, so people would probably know to put 625 here, but n is always your sample size, so just make sure to keep that in mind. If we knew the size of the population, like if they said there are, I don't know, 100,000 new brides, we'd want to make sure to use the sample size always in our calculations, not the population size. So this should be, 25,000 divided by 25, right? 1,000. Standard error is about 1,000. And then 56 says, what's an approximate 95% confidence interval for the average amount all brides in Chicago who got married in the last 2 years would say they spent on their wedding. So here, because it was random, I can calculate my 95% confidence interval. If it said that this wasn't random, the answer would be can't calculate it. And it's a confidence interval for the average amount. So the average amount was $72,000, right? And we just want to make that into a range. So I'm going to add and subtract 2 standard errors because the z-score for 95 is 2. So if you remember back from the other question where we had an 85% confidence interval, it was somewhere up here, 38, this one. We added and subtracted 1.5 standard errors because the z-score was 1.45 for 85%. For 95%, the z-score is 2. So I can actually figure this out. 72,000 plus or minus 2 times 1,000. Ooh, this one's, that makes this easier to do in my head. So this should be D. So to interpret the confidence interval, because that's the hard part, right? What does this actually mean? This means I am 95% sure that if I asked every single bride in Chicago who got married in the last 2 years, every single member of my population, the true average would be between 70,000 and 74,000. That's what that means. So confidence intervals are good. They're used a lot, especially like 95% is kind of the ideal confidence interval. Somebody said, was question 45? Why was question 45 D? Where's 45? Let's see. Oh, yeah. So 45 for this question about the 2 polls, the iClicker and the time poll. If I wanted to create a box model for the iClicker poll, it wasn't random, so that's why we can't do that. So remember, if the poll isn't random, then we can't use our formulas, we can't do a box model, and we can't do a confidence interval. Cool. Let's see. To which of the following populations can we apply that confidence interval? Remember, only our population, not any subgroups, not anything bigger. I can't say that is the same for brides in Champaign, Illinois. I can't say that's the same for all brides in the U.S., only brides in Chicago. So all U.S. brides, nah. All teenage brides, nope. All brides who got married in Chicago in the past 25 years, no, definitely not. So that's, I think I've said this probably a lot, but that's one way that people can lie with statistics. They'll take very specific data from a specific population and try and generalize it to a broader population. So beware of that for sure. All right, 60 says, let's say another poll in New York City was done by Carly Flanagan and Albert Yu. Bert used to teach Stat 100 as well. Now he teaches 400. He must have been teaching it when I wrote this. Anyway, they randomly sampled 5,625 new brides in New York City and asked them the same question. How does this standard error compare to the one from question 55? Okay. Hold on, I'm looking. I'm seeing some questions. Do you think this poll about brides is including simple courthouse marriages? Would they create big outliers obscuring the data? That's a really good question. If it's random, it probably does. But I'm guessing if that's the case, those would be extreme outliers, but there's probably extreme outliers on the other end too that are spending way more than that, like hundreds of thousands of dollars on their wedding. But that's a good question. I actually don't remember, just because I wrote this question a year ago. I don't remember the exact sample that it was from, but that's a great point. Where did you get 1,000 for number 56? Oh, from 55, right? We calculated it. Somebody already answered that. Yeah, 1,000 was the standard error we found. Okay, so here we're looking at standard errors. Okay, so n is increasing here. So basically, the only difference between question 60 and question 55 is one of them's for New York City and then one of them is for Chicago. And then the sample size increase. So as n, we know as n increases, the law of averages says the standard error for the average decreases. It goes down because in our formula, we can see up here in question 55, the standard error for the average, as n gets bigger, the whole thing gets smaller. So for this one, I'm definitely going to say my answer, it's not going to be the same because we sampled more people. It's not going to increase because if we sample more people, our our error should get smaller. And then let's see, what is the difference? So we need to decide if it decreases by a factor of 9 or 3. So if my original n was, what was my original n? 625. So my original n was 625. My second n was 5625. And so I can see how that factor changes. So if I take 5,625 and divide it by 625, I get that n is increasing by a factor of 9. So my standard error is going to decrease by a factor of 3. So this is, again, the law of averages, where if n goes up by a factor of 9, the standard error changes by the square root of that. So this exam, this fall 2019 exam, had a lot of questions about the law of averages. Like, as n changes, how does that affect your standard error? So that's something that I feel like a lot of times when people are reading polls, they kind of don't understand that relationship. If they don't know the formula, how would they know? So that's always good to think about. If you want to increase your accuracy, you need to decrease your error and sample more people. 61, if the study asked brides what percent of their income they had spent on the wedding, what would the box model have on the tickets? So percent of your income, that would go between 0 and 100, right? So numbers ranging from 0 to 100. If the poll had asked, like, did you get married? Somebody asked about like simple courthouse marriages, like, did you get married at a courthouse or not? That would be ones and zeros, yes or no. And just a few more. 62, what's the largest the STS01 box can be? 0.5, that's just a fact. Hopefully you guys remember that from the homework. And that happens when we have half ones, half zeros. Question 64 and 65. All right, it says, hint, draw my box first. I see that right away. So it says a box has 35 tickets. All right, 35 tickets. 7 are marked -2. So there's 7 of those. And then 28 are marked 6. And it says, what's the average in the SD of this box? So a final box, I guess, for this question. I'll do the average first. So the average is just going to be, we're going to add up those 7 -2s. We're going to add up those 28 6s and divide by 35. And this ends up being 4.4. So the average, again, is always just you add up all the tickets and divide by how many are in the box. And I'd recommend, as you guys are going through the exam on Wednesday, to definitely draw your boxes. That's going to help for sure. What's the SD of the box? So here I can use the shortcut formula because there's only 2 types of tickets. If there were more than 2 types of tickets, then I couldn't use the shortcut formula. I'd have to use the long formula that I said I wasn't going to have you guys do. But here I can use the shortcut formula. Formula is just the absolute value of a minus b, so -2 minus 6 times the square root of the fraction of -2, so that's 7 out of 35, times the fraction of 6's, which is 28 out of 35. So I have absolute value of -8, so 8 times that square root, and that should be about 3.2. 8 times that fraction. And then that is the end of the practice exam, and it's 8:29, so I feel like it always takes me about like really close to an hour and a half to do all these. But like I said, you guys will probably go much faster because I was explaining all of them, but you should have plenty of time for the exam on Wednesday. It is 63 questions, 63 or 64, so really similar length to this. There shouldn't be any surprises on the exam. Should be really straightforward. If anyone has any last minute questions, I'll stay on for a few minutes, but some people are saying thank you in the chat. Thank you guys so much. It's always fun. I miss being in person, so these live reviews are really fun. And thanks to the TAs. Yes, thank you so much. Have a good night. I hope you guys are okay with the exam, and good luck studying, and good luck on Wednesday.